Hi everyone, Tricia Cease here. Thank you for joining us on the webinar today. We're going to be talking about filament printing tips, tricks, and troubleshooting. So you'll get lots of great information about 3D printing our metal and ceramic 3D printing filaments through your printers. So I want to introduce who we have on the call today, and then we will get started with our agenda. So helping us out with the topic today are David Lawson of Sapphire 3D, who has done lots of printing and sintering with our materials. Brad Woods, that photo in the center, he invented filament. So he's got pretty intimate knowledge about using it, how it prints, and what you can do with it. And then of course, myself there, I'm the president of the Virtual Foundry. So as the webinar goes along, please type your questions into the chat box. We will have a Q&A period at the end of the webinar. The webinar is being recorded and the video will be posted to YouTube after it is completed. I will also send you a follow-up email with all of the resources that we talk about today and a link to that YouTube webinar so you can rewatch and find that information if you missed it the first time around. Any questions that we don't get to in our time today will be answered by a follow-up email as well. So don't worry if we don't get to your question, we will still answer it for you later. So the agenda today, we're going to talk about the basics of filament, what it is, how it works. We're going to give you the setup of printing tips and tricks, along with some insider info on getting successful prints. We'll go through some troubleshooting, how to spot when things aren't right and what to do about that, and how you can repair or clean up your prints after they've been printed. We'll describe the rest of the full metal process if you're interested in getting full metal parts out of your FFF 3D printer. We'll give you some resources, as I mentioned, to help you get started and to help you as you're going through the printing process. And then finally, it's Q&A time. So let's dig in. Starting with Filament Basics. You can see here a chart of the materials that we have available. All of these materials use the same basic recipe. So it's that base metal or ceramic, aluminum, bronze, copper. And then the same binder is used in each of our materials. They all go through the same manufacturing process. Now they each have different percentages by mass of material loaded into the filament. And you can learn more about that in the podcast that we released yesterday that talks about how filament is made. And in that podcast, we talk about the powder that we use, what properties that powder needs to have in order to make a successful filament, how this whole thing even got started, and then as well as some of the basics of its use, some of the properties of the material itself, how to manage some of those properties. So lots of good information in that podcast from yesterday. We won't get into those powder properties today and sort of what goes into making the filament, but you can get that information there. And again, I'll send you a link to that after the webinar today. So because they use the same recipe and the same general manufacturing process, they're also going to print the same. Now, filament is made of a metal or ceramic powder and a plastic binder. The plastic binder that we use is PLA compliant. So that's why they print very similarly to PLA. You're going to follow the same basic settings with some tweaks and some special tips to help you get a successful print. But it's really going to, if you're familiar with printing with PLA, this really won't be much of a leap for you. So let's learn about, or let's talk a little bit more about how filament is different. So Brad, I'm going to hand the mic to you here to talk about how filament is different from other 3D printing materials on the market.
Sure. So the key difference is that it's with different interesting materials. Things most frequently are the metal powder. So essentially what it is, people tend to picture a plastic filament with some metal in it. But when you right down to it with a microscope, it's kind of the other way around. It's it's metal powder with just enough plastic coating the outside of it to stick them together into a string for filament, so that it's strong enough to get through the 3D printer. So the key difference is that in the end, you can wind up with a pure glass metal part. The PLA gets removed during the debinding process, and it becomes a rigid object. The particles weld together during the sintering process. So, those are the key differences.
All right, thank you. So now we're going to talk about the equipment and the supplies that you need to print. So you need an FFF or FDM 3D printer, and that's going to be any FFF or FDM style 3D printer that accepts third-party materials, which is going to be nearly every brand. So as long as your printer can print any kind of filament or any brand of filament, you'll be able to print Filamet metal and ceramic 3D printing filaments. Direct drive typically works better than boat and tube, but boat and tube can work as well. And you'll need a stainless or hardened steel nozzle sized at 0.6, a 0.8 millimeter, a Filawarmer, and you do need to manage bed adhesion because filament really sticks to the print bed. So on a glass surface, you can use a glue stick. On every other surface, we recommend using blue painter's tape. And then you'll also need your filament. So that's it. You're not making any modifications to your printer aside from getting that harder nozzle. Now we'll walk through the print settings here, and Brad, I'll hand the mic over to you again here to talk us through each of these items.
Okay. So the Filawarmer is a very simple device. It sits at the edge of the spool. As the filament comes off the spool, the Filawarmer warms it. Specifically, it takes it to about 65 Celsius and oscillates between plus and minus 10 degrees Celsius in that range. That does a couple things. Most importantly, it takes the memory out of the plastic that it gained while it was on the spool. Otherwise, the material would continue to want to be in that circular shape. So the Filawarmer relaxes that and straightens it out. It dries it a little bit, and it PLA can be annealed somewhat, so it actually causes the material to become stronger. So the setup that we recommend is to hang the spool directly above the 3D printer, about 12 to 18 inches above it, with the Filawarmer right, nearly in contact with the spool, at an angle that's tangent to the center of the from there, you want enough distance between the Filawarmer and the 3D printer that when the head moves, it's not pulling dramatically. You want a longer sweep and a more gentle angle on the material as it's coming out of it. Our material is not as strong as plastic. It isn't going to be. It can't be. It's loaded with so much additive that sort of the key struggle in manufacturing over the past few years was developing a polymer that would hold the material together well enough that it could be handled, yet have enough metal powder in it that it will sinter properly. So once you get it through the Filawarmer, though, it's quite stable, and it will make it through the printer.
We mentioned the nozzle earlier. You're going to use a stainless or hardened steel nozzle sized at 0.6 or 0.8 millimeter. The harder nozzle is important. A brass nozzle will work, but it will wear down pretty quickly, and then your print will begin to fail. So the stainless or hardened steel nozzle will stand up to the materials much longer than that brass would. And we recommend that little bit larger size at 0.6 or 0.8 just to help with the printing process. Now your print heat settings, some people think that you're actually going to try to melt the metal as you're printing it, and they think they need to have a really hot printer. That's not the case. The only thing that you're melting during printing is the plastic. So your printer nozzle only needs to get as hot as it needs to melt the plastic. So that's going to be a range of 205 to 235 C. Your print bed will be at a range of 40 to 50 C. So one of the things that you can mess with or tweak or adjust as your printing is happening is the nozzle temperature, because that can affect the flow. So we'll talk about flow rate a little bit more later. We talked about build plate preparation with that blue painter's tape or glue stick on a glass bed. Brad, tell us about print speed and how you recommend people start out.
Right. We recommend that people start out slower than they would with PLA. And you can speed up quite a bit, but it's just easier as you're becoming familiar with the material. If you go slow, watch it closely, and watch the bed. The nozzle height is a key problem that a lot of people run into. Our material is really viscous, so where regular PLA would easily squeeze through the nozzle if the nozzle was in contact with the print bed. If you can kind of picture that, with our material, it will completely clog it. And people often think that their nozzle is clogged, but in almost every case, the situation is more like the print bed is too close to the nozzle. So they just need to back off slightly.
Okay, we're going to give a little bit more information about layer height as we go along, and Brad has some pictures to share with you later. We're going to talk a little bit more about flow rate too. So what I've learned as I have practiced 3D printing on my own is that flow rate really has an effect on the quality of your print. And a flow rate of 100 is really an arbitrary number. It doesn't necessarily mean anything. So adjusting that flow rate to higher or lower is totally fine. You won't hurt anything as you experiment with the different print settings and how they affect the quality of the print. Now, support materials. If you have a dual extrusion printer, you can use any sort of secondary support material that you would use with standard PLA. So those water soluble ones, you could even use regular PLA as your support material. You can also use more filament as your support material and then break that off before you go into the sintering process or before you polish your print, whatever your next process is going to be. Okay, now we're going to get into the troubleshooting portion. So Brad talked a little bit about spool placement, but Brad, expand on that for us a little bit. What happens if the spool is sort of off at an angle, or if the print has to go around, or I'm sorry, if the filament has to go around a corner, and how important or the role that friction plays in that?
Right. You want the spool to spin freely as possible. Any tension on it is just gonna make it more likely that you're going to have problems. So you can download an STL of a spool we have that fits around a piece of 1-inch PVC. We also sell just a very simple PVC spool holder with an adapter that minimizes the friction. And your general objective is to make the path from the spool to the printer just as simple as possible, as straight as possible, and with the fewest bends possible.
Okay, we talked about webinar installation and Filawarmer installation and the role that the Filawarmer plays. It's also important to allow the filament time in the Filawarmer. So we do have 2 videos, well, 3 really, on our YouTube channel. One is talking about basic Filawarmer instructions, and that's going to show you some good spool placement and Filawarmer lineup. The one that is referenced here, Filawarmer setup part 2, is going to show you letting that filament sit in the warmer for a few seconds before you pull it through. And that's really going to apply as you're getting started. Once your print is going, the Filawarmer is going to flow, the filament is going to flow through the Filawarmer at just the right rate. And then third is we have a very short video that shows how a filawarmer can be set up with a Ultimaker machine, or a machine where putting the spool of filament above the 3D printer just really isn't practical. You can look for that for an idea of how to set up your filament and your filawarmer to go into a machine like that. Now let's talk about under and over extrusion, because this is pretty common. And here we do see folks send us in pictures of prints, which is great. Please send in pictures of prints. That gives us the most information for us to be able to help you. So we do see prints that are under extruded quite a bit. And you can, looking at these photos, the two on the left, the very light one, and then the one in the center, which is bronze, you can see the pieces on the left are under extruded, and its mirror piece right next to it is perfectly extruded. So you can see the difference there, and how under extrusion looks like it's just kind of holy. Then that third piece, which is that darker one and that copper, that one is very much over extruded. So, and then you see a screenshot from our Cura slicer. So Brad, sort of talk us through that and how you can correct those things as your print is going along.
Right. Our material, as a result of having so much material added to it that isn't a thermopolymer, is it's very viscous. The analogy we use is it's more like bread dough. So it takes longer for the material to flow through the nozzle, and it takes a bit more force. And we found that if you simply exaggerate the flow rate by 5%, you generally come up in about the right space. I would say the number one most common problem that people have using our material under extrusion. And the solution is to simply exaggerate the flow rate.
So you can see in the screenshot that we have here, the print that I was trying out, I ended up at a flow rate of 125. So again, that flow rate number is really kind of arbitrary. So it's not going to hurt anything for you to raise that number above 100. Your printer won't know you're not doing anything bad. The next troubleshooting topic that we're going to cover is nozzle clogs. So this is something that people very commonly write into us about. So Brad, walk us through, first of all, what can cause a clog, how to know whether it's a nozzle clog or something else, and then what to do about it.
Okay. Generally speaking, Virtual Foundry products don't clog nozzles much more frequently than regular PLA does. The particles that are in it are, less than 1/100th the width of the opening in a 0.6 millimeter nozzle. And what happens is the most common problem is people will put the nozzle too close to the print bed. So essentially the print bed is blocking the nozzle. And there are a couple different things that can kind of mimic what looks like a nozzle clog, but it's actually not. One that I just described is the most common. The next most common is worn drive gears. And this is a situation where either people don't have the pinion gears, the drive gears tight enough, so the material slips past it, or gears are simply worn out. A lot of printers come with brass gears, and they do wear over time. The equipment that we use in-house, we've settled on dual gear micro Swiss heads, and they work great. And I'm gonna try to share a photo here. Let's try. Okay, Trisha, this is gonna stop your screen. Okay, so this is from one of our Ender 3s that has a lot of miles on it, so it's looking a little rough. But you can see the dual gear system from Micro Swiss. There's a few of them. I can't think of the other one, but we really like the Micro Swiss. This works great, and it's affordable. The common problem is that this gear is either not tight enough so that it doesn't push the material forward evenly or consistently, which will cause an under extrusion, or it can also mimic a nozzle clog. You think their nozzle is clogged because the material's not moving forward, but that's not exactly the cause of it. So tension too low in this situation can cause a problem. Conversely, it can also be too tight. There are some of these devices that will let you over tighten it to the point where you're crushing the material and it can't move forward because of that. And
hey, Brad, as you know, I use the direct drive as well with the dual drive with the Prusa.
right.
I get asked a lot about the Bowden style, or at least the style where the drive is farther back. Do you have a lot of experience with that?
Well, we have an Ultimaker 5S that we use regularly and successfully. So yeah, and actually we have quite a few users that use Bowden tubes.
Right.
Internally, we've just kind of settled on the direct drive units. I think it's just kind of easier to manage.
Yeah, okay. Yeah, I just don't have experience with those. I do have a lot of experience with the direct drive.
Right. No, we've used them, but yeah, we prefer the direct drive. And I want to talk this is a nozzle, and this is a case where if you were to start printing right now, it would mimic a nozzle clog, but it's clogged, but it's clogged with the bed being jammed into the end of the nozzle. When you're setting up, you should have, here I have another photo. You see a little bit of air between the two. And we also recommend that you exaggerate the thickness of the first layer. Like if you're printing at 0.15, try 0.25 and give yourself a little bit more margin of error.
Yeah.
And what will it look like if the nozzle is too far away from the print bed on the first layer?
Oh, I should have taken a picture of that also. It will look like a little pile of strings on your print bed. And it looks just like a crumbling mess. So it's a little bit difficult to describe. This piece here, like this broken chunk over here, you'll wind up with piles of these. And right. And if it's too high, obviously it can't work either. The balance is delicate, and you don't have huge. This isn't material. This is 3D printing in general. I think everyone struggles with bed leveling when they're getting started.
But I do have to say that I've done a lot of prints with your materials, and all the materials pretty much. And that's probably the number one thing that I've had to like. And once you get it set, it's set, right? But the nozzle height, to me, is the key also to getting the right flow.
Yeah.
So that's something right away. Even if I haven't used the printer in a while, the first thing I do is check that. So.
Okay, we did get an answer that I'd like to talk now. So we're going through some troubleshooting, and the question came up, what we're talking about here, is this valid for all of our materials, or do some of the materials perform differently?
No, this is pretty standard for all of our materials. Some it's a little more severe than others, but generally speaking, all of our materials are very viscous and doughy.
And Brad, your sound is cutting out a little bit. Would you please talk about the suggested thickness for the first layer again?
Okay, yeah, I'm getting warnings that I'm having internet connection problems. So, right, what I like to recommend is on the first layer, when you're setting up your slicer, make the first layer a bit thicker, maybe 0.1 millimeters thicker than you're going to do the rest of it. It just gives you a little bit, that fraction of a millimeter as margin of error, and can make it a little bit easier for you.
Now, there are legitimate nozzle clogs that can happen. So if your nozzle temp is too high, it's going to burn that plastic out of there. And then you're left with a big chunk of metal in your nozzle. So that is a legitimate clog that can happen. So you're going to keep your printing temp between 205 and 235 C. There's a little bit of a margin of error because sometimes the nozzle isn't exactly the same temperature as what your slicer program is saying, or even what your printer is saying. But keep that nozzle temperature within that range of 205 to 235.
And this is something we've experienced repeatedly, is the actual temperatures on the 3D printers vary much more widely than you would expect. It's pretty common for them to be off by 10 and 15 degrees Celsius. It's fairly remarkable.
Hey guys, what about retraction?
Yes. What we recommend is a small amount of retraction. So like less than a millimeter. And we think what happens is as it gets pulled back, it minimizes the clogging. For whatever reason, adding a little bit of retraction to your slicer settings it just makes it run a little bit more smoothly.
What does retraction do?
It pulls the filament back up into the hot end. So normally the extruder is pushing the material forward. The retraction will just pull it back a little bit. And the back and forth motion just kind of, it minimizes the number of times you'll experience a clog.
All right, thank you for that. Next, we're going to talk about how you can sort of finesse your print after it's done. If you've got a little bit of over extrusion there, or something on the side of your print that you want to kind of clean up or repair it. Brad's going to walk us through some ways that you can do that.
Okay. Our materials, whatever shape you can get them into and however you can do it, you can turn it into a metal part at the end. So you can literally do freehand metal with a 3D pen. And I have some examples here. So this is just a 3D pen that we got off of Amazon. These are $50, something like that. And when you run our material through them, I think I have an example of that one here. So this is just a piece of and a 3D pen. And augment prints, you can use it like you would use TIG welding. You can use it as a filler. The other thing we like to do here is a soldering iron. So you can also get these nice soldering irons in adjustable temperature. So I set this one to 210 C and it'll just hold it there. You can use that to weld multi-part prints together, fix flaws, clean things up, things like that. And this is the soldering iron that we use. And again, very inexpensive. They're maybe $30 or $40, but they work extremely well. Another indispensable tool, X-Acto knife is nice to have around for cleaning up. You'll always wind up with little chunks. This is not a very good print, but you often wind up with, we call them slubs, little chunks of material that build up on the edge of the nozzle and then come loose. So you can just pick them out with an X-Acto knife, or dental tools work very well. In this example, I'm just using a rasp, a coarse file. And there's kind of an interesting effect. Enough metal in it that just this piece was just ladled, and it starts to look like metal after a little bit, even before it's sintered. And we have some users that actually, use it in this state. It looks enough like metal that you can pass it off. So it works for props and things like that.
Okay, thank you for that, Brad. Next, we're going to talk about what to do if you want a full metal part. So the basic process of getting a full metal part from your standard FDM FFF 3D printer is that you're going to print with any printer that accepts third-party materials. You're going to debind thermally. There's no separate process or equipment required for that. You'll bury the part in a refractory ballast, and then you'll sinter the part in common kiln equipment using sintering carbon to absorb the oxygen in that process. So you want to be sure to avoid oxygen getting to your part during that sinter process. So that's the basic of getting full metal from your 3D printer. David Lawson, who was on the call and has said a couple of things, has the most sintering experience of all of us. So we do some sintering here in-house, but David really has made an art out of the process. So if you are curious about what sintered parts look like, or you want to get your own part sintered, you can talk to David at Sapphire 3D and he can do that for you. We are also working on getting some of those rectangular, the Virtual Foundry logo pieces sintered up and ready to send out to people if you would like to have a sintered part in your hands to see what that's like. Now, Brad included a link to the photo album that he was showing in the chat, but I will also include that link in the follow-up email that I send. So what should you do if you are trying to print and having some troubles, or if you want just some more information before you get started? We've got a YouTube channel that has a couple of other webinar recordings out there, and that's the same place that this one will be this afternoon or tomorrow. So we've got one that's getting started with FFF metal that talks about the printing process, the sintering process, or the debind and the sintering process. So that's more of a general overview. And then we've got one that's all about sintering filament. And that one includes a demonstration. The demonstration window is small, but it's there. And we've also got a series of short instructional videos, those ones about the Filawarmer installation, a cool video that Brad put together of his prototype experimental metal injection molding trial. So he's really excited about the possibilities with metal injection molding and where that can go with this material.
Right. I wanted to touch on that a little bit more. Early in the presentation, I said that however you can get material into a shape, it can be sintered into a metal object. So in the example in the video is we 3D printed an injection mold, and then we take the same material and inject it to that mold and replicate creating metal parts. It's kind of an interesting experiment.
That's cool.
Our website also has a page called How to 3D Print Metal that's going to talk about printing, debinding, and sintering, and gives full instructions for those three processes. We have sintering processes that were established by David at Sapphire 3D for copper, bronze, and our three steels, the 316L, 17.4, and the Inconel, as well as the Amico clay ceramics. So instructions for the sintering process are included on our website for those. Sintering processes for other materials have not been developed yet. But if you look at that How to 3D Print Metal page on our website, you'll find the full instructions and lots of what we talked about here today. Not as much of the troubleshooting, but you can always contact us for support, info@thevirtualfoundry.com. It's always really helpful if you send in some photos. That helps us diagnose the problem much more quickly. And also, it's really important to experiment. So this is all about a trial and development. It's a developmental process. So, it's a brand new thing in the world. So you got to try stuff out, tweak your settings, adjust your flow rate as you're going through, adjust your nozzle temp as you're going through, and just see what the results are.
And we'd also encourage people to share their experience, new things that you found, better ways to use the materials, better solutions for sintering. let us know, and we'll put the information back out to everyone.
Okay, so I'm just getting we're ready for the Q&A part. I'm getting those questions ready. So Brad, I need you to riff for just a couple minutes.
Okay.
Hey, I got a question for Brad, and in general, you guys. I noticed on the first slide there was, it talked about the percent metal. So most of your products, and my experience has been there in the 85, 90%, maybe even higher now. But the clays are still 40%. I know you mentioned in the past you may try to boost that up. Any idea when that might be, or when you might be thinking about boosting up the ceramics?
Right. Yeah, actually, we just the last week we started working with 3M on a project to bring some of their industrial ceramics online. So the materials that we make right now are made from Amico clay, which is basically, it's the same clay they use in schools, grade schools, what you would use for pottery.
Right.
And part of our limitation, how high we can go, is particle size. So we have no control of particle size when we're dealing with that sort of industry.
Okay.
But working with 3M, we can specify. So we expect to have samples in next week, and we hope to start rolling out new versions of the ceramics probably over the next couple months.
I think even the ones you have, I mean, I've only done a quick and dirty sinter process, but the clays come out really nice. I mean, they sinter really well, and there's no need for refractory or any carbon or anything. It's just like normal ceramics. You just stick them in a kiln. So anyway, pretty excited about your ceramics. So excited to see where you take that. And they're very, they can handle very high temp. You know, I've taken my ceramics the ones that I've made, and I've put them to a torch. And so there's probably some pretty high temp ceramic applications out there. That's all.
All right, thanks guys. Thanks for asking that question, David. Now let's get on to a few of our attendee questions. Do you have example images of filament microscopy or better material percent per cross-sectional area?
I don't have a picture of the filament. I do have a picture that will probably be interesting. Here, hang on a second. Okay, share screen. Okay. I don't have a photo of the final filament handy, but that's interesting. This is a ceramic at a microscopic level. So this gives you a very good idea of what's going on. And this blend of materials, well, it's all one material, but the blend of sizes is intended to maximize the amount of material it can fit into any given area. So literally we've tweaked the distribution of the particle sizes to enhance that property.
Okay, thanks for that, Brad. Our next question. Have you tried to print materials like PC or PA6?
No, I'm actually not familiar with either of them. But what we've done, and like I've said before, this has been a 6-year quest to get us to the point where there's enough metal in the material that they sinter well. So essentially, we've been working with the one binder. It's the binder that we call it PLA compliant. Moving forward, I expect us to start experimenting with other binders, other medias, nylon, things like that. The questions are coming up more and more often. I expect us to start moving in the direction of different thermopolymers in the near future.
Okay, next up, we've got a user trying to use the ZMorph VX 3D printer. It's a direct drive. Has anyone had experience with metal printing with that printer? Brad or David, have you heard about any other of our customers using the ZMorph?
I have not.
I have not either. But I mean, if it uses filament, it shouldn't be a problem. We always qualify this statement. It'll work in any printer that uses filament. The reason we don't state it that clearly is there's a handful of FDM 3D printers that won't let you use filament from other manufacturers. So it's sort of like, you know, the inkjet concept where HP wants you to use their inkjet cartridges and not someone else's. So, but generally speaking, any printer that uses filament can print our materials.
Okay, how about the motion system you use for printing?
I'm not exactly.
I think this may go with the next question. The same person wrote them in. Planning to print the aluminum from Prusa, and it's not precise enough.
Well, our general take on printing technology in general is that we don't get very far into the 3D printing end of things. This is, you know, it's its own technology. It's improving as time goes by. And as it improves, the application of our material will also improve. But we've been pretty careful about staying out of the 3D printing technology itself.
David, you are using primarily Prusa printers. Have you printed aluminum with those?
I have, but it really depends on what the question is in terms of what they mean by precise enough.
Right.
If you're trying to compare something to a machined part or something like that with machine part tolerances, I think just in general, 3D printing is not going to compete with that. But 3D printing will blow the doors off machine parts and creating unique geometries and things like that. So it really depends on the application.
Right, and this is another recurring theme. It'll likely be, the ultimate solution will likely be a near net shape type situation where you 3D print the rough object and machine it to, if you need very, very high precision, you would then machine it to that level of precision.
Right, I agree.
Okay, guys, tell us about shrinkage during sintering per type of filament.
I mean, oh, go ahead.
No, I said you can take that one, Dave.
Oh. No, I mean, I sort of on bronze and copper, it's gotten to the point where, you know, I typically will quote a 5 to 7% range. You know, it does vary depending on the part geometry by the X, Y, and Z. Although recently I've been experimenting with some things that are, the Z would typically, so when the part is sintering or debinding, you get sort of a degassing as the plastic burns away, and sometimes that will sort of elongate the Z. The part will actually grow in that direction, or depending on how you do it, it could shrink more in the X and Y and than it does in the Z. But I've recently been doing some work on some things where I've been able to get more consistent results. So on bronze and copper, I would say it's probably in the 5% range. The stainless steels, I would put more in the 10% range. And part of that may be just the fact that to sinter those, we're at a much higher temperature range, so.
Okay, another, a final part post-sintering question. When I sintered the copper, I was left with a crystal-like look on the outside. Would that clean off with just a polish, trying not to take any materials away from the object?
Right, and I think these might be the pictures that you and I were looking at yesterday, Trisha. That's the one of the
like
first.
that. I mean, the user can't respond, but that's like a crystal. That's like a, look, where'd I go? So from my perspective, yeah, if you just then put it in a little rock tumbler, or you can do other things, it'll polish really nice. I don't know that it removes material.
Right. It should just burnish it. So you're basically knocking off the high points and lowering them.
Right, right.
But a user sent in some photos yesterday that had, it was either copper or bronze, and it had really distinct crystal growth in a way that I've never seen it before. And actually, we were looking to set up a phone conversation, so I would kind of like to know how they got there. It likely was fired too warm, but it still was very interesting.
How about the viscosity of the filament?
It's high. And the analogy that we've been using is if PLA is cake frosting, our material is bread dough. So that's part of why you need to exaggerate the flow rate a bit. It just takes, the reality is it's just very viscous.
Have there been any thorough parameter studies in order to standardize all important processing parameters?
No, is the short answer. I doubt. It's so hard to say. So other companies that are tackling this problem, for example, if you look at Desktop Metal or Markforged, what they're doing is building these things into the slicer software. So they're limiting the things that you can do in order to provide consistency on the output side of things. Our strategy has been kind of the opposite of that. We've focused on a completely open architecture type environment. So as people are developing standards that they're using in-house, yeah, that's happening. So we have users that are developing processes that they use for repeatability. But I'm not certain that those will be even relevant to other users as we go along. I'm not sure.
Right. So because our material allows for that flexibility in hardware, you have control over every part of the process. Now, we have been able to set up some general processes that give you a jumping off point, like those printing parameters that we discussed earlier, and the sintering process that we have posted on our website that David developed. Those are all great starting points for you to begin to work with the material in your own system to get the results that you want. We're always here to support you through that. We do have a couple of other questions that have come on that I wasn't able to get onto the slide. So how close are the final mechanical properties? Do these parts get to the same material produced conventionally?
Okay, this is another recurring theme, and it's very difficult to draw a direct comparison between 3D printing and machined parts. And this isn't just Virtual Foundry materials. This is just 3D printing in general. It's just different. So we're hoping, and what we're starting to see is people are starting to think of these parts in a little bit different way. It's a new way to solve problems. It's just very difficult to draw a one-to-one comparison with machined or cast or forged parts. What do you think, Dave?
Well, I mean, we've done a few studies and people have requested, some tensile bars and tensile testing and trying to look at comparisons to ASTM tensile testing. And it's always going to be lower right now in terms of the strength. Part of the reason I explain also is that 3D printing has a lot of voids and air gaps. And then in general, once you sinter it, there's going to be tiny microscopic cracks that maybe a machined part or a cast part may not have those to that extent. But it's very early And there's a lot of work going on to increase the density of these parts. I myself am doing a lot of just testing and studies with the goal of increasing the density in both ways, the density of the green part before you sinter it, and then the density of the part post-sinter. So I think we're at the bottom of the first inning on this. And I expect that we may not get exactly a match, but we're going to get closer to those strengths. It's just, it's going to be a matter of time.
Right. And more research is coming online quickly. So we have customers in healthcare working with titanium body implants. So the go-to strategy is hot isostatic pressing. So after that type of processing, you know, it's going to be, the parts are going to be different than what we have right now.
Right. And just in general, I think that having said what I said, there's a lot of stuff you can take a part that's produced conventionally and look at its functional requirements. And then with 3D printing, you can say, well, what are my design constraints? Can I design this part a little bit differently? And in that process, you may actually strengthen the part with the 3D printing process. And so that's kind of the mindset you got to think of, is not just to create the same exact part, but do you have the ability to make some changes in the design process so that you get a better outcome sintering.
Right. And a lot of this is becoming automated, which is really exciting. So on the generative design side of things, people are creating CAD drawings, but rather than drawing the whole part, they'll illustrate the load points and then tell it how much load is on a specific point, what angle, all those parameters. And then you have the software generate a design for you that solves that problem. So it uses minimal materials. It looks unlike anything, you know, that the average human would sit down on a machine, because they have a very interesting organic look to them. But that side of 3D printing and the design for 3D printing is going to have a big effect on part quality and application as we go forward. And it's just getting started now.
Yep.
Now that's one of the things that makes me most excited to be in this field. So it's very natural to think, hey, can I now 3D print this part that I always had machined before? But we need to be asking broader questions. What new things can I do with this technology? And as David mentioned, how can I change my setup? How can I change my part? How can I change my assembly to make 3D printing the best use for manufacturing this particular part? So as we move forward and 3D printing becomes more pervasive and more applications are discovered for it, things are going to start to look a little bit different. And other things will come along that we haven't seen before. So expanding our viewpoint from just trying to replace machined parts is very important as we think about the future of 3D printing. So I do have one more question before we wrap up. On our website, our users have found printing speed, some of those basic setup things that we talked about, extruder temperature, bed temperature, but they're not seeing something that talks about flow rate and layer thickness according to the specific nozzle diameter. So we're talking about using 0.6, 0.8. Does that, or even 1.0 millimeter, does that nozzle diameter affect how you're going to start your layer thicknesses and your flow rate?
Do you want to try to tackle that one, Dave?
I was going to have you address
Francesco, you tripped him up.
I pretty much am keeping.
Great question.
I'm pretty much keeping my setup the same, and I've had success with my 0.6 nozzle. I do use a 0.8 to 1.0 for the high carbon iron, but in general, I have my 0.6 set up, and I'm able to use the same kind of flow rate and all that stuff for that, and same layer height.
From a strictly logical standpoint, it shouldn't matter, and it should be compensated for in the slicer. But the reality is that the slicers are created by humans, and like, again, we're on the very front end of this stuff. The best solution I've found is to exaggerate the flow rate.
Well, great questions, everyone. That wraps up our time today. You can see on the screen here ways to contact the Virtual Foundry and Sapphire 3D directly. I will also send a follow-up email with all of the resources we talked about today, as well as a link to this webinar that will be posted on our YouTube channel later. So look for that to come to you from me either this afternoon or tomorrow as we wait for that video to process and get posted. Thank you all for joining us today. I know the webinar had a lot of information, so go forth and print and let us know how that goes. Thanks, everyone.
Thank you.
Thanks, everyone.